So thank you very much for the introduction, the kind invitation here. So as you said, my main interest in research is software. So I'm interested in what is software and how to build software. So I try to share my view on that. And first, starting with a very high level overview of what really is software. So I would like first to compare the process of writing software with the process of creating a scientific theory. So just, probably of course you're all scientists, so you already know that, but to make sure and to agree on definitions, coming from the Stanford Encyclopedia of Philosophy, there is this notion of scientific theory as an explanation of an aspect of the world that can be repeatedly tested in accordance with the scientific method using a predefined protocol of observation and experiment. And so the scientific method involves the proposal and testing of hypotheses by deriving prediction and so on, and then performing this experiment to see whether the preconditions are valid, the predictions are valid. And so we see this notion of the model being central to scientific theory because the model is an abstraction of an aspect of the world for a specific purpose. And thus, any scientific theory is a model. The reverse is not true, of course. There are many models that are not scientific theory, and I'm not going to be too controversial, but I didn't mention astrology or homeopathy or the like, but you see what I mean. So my point is that nowadays creating a scientific theory is writing software. Actually, it's even more writing software. Because the fact is that in the past, up to the 20th century, mathematics used to be the language of science. When science was simple enough for math to handle it, basically. If you look at a very simple example in physics, such as Newton gravity theory, if you have two bodies, then there is a theory explaining the universal gravity, and then you have an analytical solution for that can be produced through mathematics. And of course, if you have this analytical solution, then you can solve the system, and that's beautiful. But as soon as you have a third body in the picture, as soon as you have three bodies, then there is no analytical solution for that. Okay? So the only way to predict the evolution of a three-body system is actually running a simulation. Okay? And so you can do it by hand, of course, but it takes a long time. So what is possible now with computers and software is that you do it within computers and you simulate it, and then you can have the evolution of galaxies and the like using computers. So my point is that as soon as the problem is complex enough, then mathematics is not able to handle it, and then you resort to software and computers. And most of the science, and that's a big move that we are seeing nowadays, is that in nearly all the sciences, there is this movement toward having computers and software as the language of science for providing models, making predictions, and checking these predictions. Okay? Of course, it does not mean that math is to be forgotten, because math is still there. I mean, when you're doing this simulation, actually the base operation, the basic operation are based on mathematics, of course. Okay? But to make it possible to have the result, you need software and computers. So creating a scientific theory nowadays, building a scientific theory is writing software. And I would say that conversely, writing useful software is really like creating a scientific theory. Why? Because you typically, when you have to build some software somehow to fit some purpose, some need, some requirement. So you have to start with a problem in the world, in the real world, okay? And then you have to understand this real world, to understand what are the rules, what are the laws, and what is there. And typically what you do is that you build a model of that, okay? Like in science. The model is not just there because the model is one thing. The other thing is that if you build useful software, the software must do something. with respect to this model, must do some computation. So we have something that we can call a function, a functionality of the software, that somehow you mixed, you compose with the model to get what you want the software to do. Okay? But that's what we call software. But the software by itself is useless unless you have a computer to run this software. Okay? And so you have this notion that Jackson's called the machine, which is made of the computer running the software. So, and the software for me is the composition of the model of the world with some functionality that I denote with this X being an operator. Okay? So here I have a machine that does what I want to do with respect to the world. But then the question is, does it do what I want? Which is the same question that scientists are asking. Does my model conform to reality? Is it possible to make prediction that I can check on, with respect to reality? And so what I do, of course, is that I'm going to test it with respect to the world to see whether my software is useful and so on. So the process is really similar of creating a scientific theory. So there is a big parallel there that is very important, and I will get back to that. So this notion of the world and the machine comes from Jackson. And if we look at history of when in history some software has been introduced in several domains, it always follows the same story. First, it's there to model the world, to provide a kind of simulation. Let's take in business, in telecom, the first software that has been written, or even with weaponry. I mean, one of the very first software that has been written was to compute the angle of guns for navy ships. So it's really to model and to know stuff about the world, to mimic what's going in the world. Okay. The second step is that once you have this model, you can say, oh, but I can connect this model to the real world by using sensors that provide real information extracted from the world and populate an instance of my model into my computer. And then I can ask questions to my model, not just in an abstract way, but with respect to what is actually happening in the world. So the second step is monitor. Okay. The third step is that as soon as you can monitor what's going on, then you can control. It means that you can run some computation and then act on the world. Okay. So once again, it's the case in all this domain that at first you can simulate, for instance, in telecom, and then in the end you compute and then you switch and you do some packet switching with software. So this is the typical evolution of when software is entering one particular domain. And then there is something which is not the purpose of this talk, but it's worth mentioning here, which is that sometimes the evolution is that the machine and the software becomes the world. Okay? You already know that because you know the notion of bank account. In the past, the notion of bank account, it's a box where you put your money, and then you put that in the bank, and there is something, and the bank is keeping your money. But of course, you know that nowadays it's not really money. It's just some information or some data somewhere in some computer. Okay, so the notion of reality of money in the bank does not really exist. It's just software. If you look more recently at the notion of a free hotel room or a free seat in a flight, okay, if it does not exist in Expedia or that kind of websites, it does not really exist because you don't know it does exist. Okay? And because you do not know it does exist, it means that really for you it does not exist. And that's somehow a danger because the reality that you see is actually provided by these people such as Expedia and the others. Okay? So it becomes the reality that, and there is no way, or it's not really that there is no way, but it's very difficult for you to find the real reality behind the interface that is provided there. Okay. But let's that's not the topic of this talk, but still it's interesting. Well, there is a big caveat here, and it has been already mentioned by other people in today. First, so a machine is made of a computer, a model, and a function. The first thing is that a computer, if you look modern processors, actually nobody knows any longer what they are doing. Okay? Of course, if you're running some logical computation, you're pretty sure that it's going to produce the right result, provided there is no bug there. For floating point arithmetics, it's already a little bit more difficult. And if you look at stuff such as how much time does it take to run this computation, how much power does it consume, actually it's completely non-deterministic and nobody knows. Okay, so what the computer is doing, what the processor is doing, nobody knows really what the processor is doing. Then the model, by definition, it is an abstraction of an aspect of the world, meaning that it is wrong. It is always wrong. It is incomplete, partial, and wrong. Okay? And then the function, it's what the user, what is the purpose of your software? The problem is that most users do not really know what they want. And this is one of the reason why methodologies such as agile kind of stuff is very helpful, because it helps users discovering what they want by receiving many feedbacks during the construction of the software. And if you try to formalize that in the term of real requirements, actually in the end, most of the bugs in a computer software are traced to bad requirements. So you do not know what the processor is doing, your model is wrong, and your functionality is not good. Okay? So are you serious? Do you really want to board this plane? Okay. So what's the solution? Well, it's not original, it's there for decades. Actually, it's the goal of software, the way we build software, is by leveraging two big ideas in science, which is abstraction and separation of concern. So we need abstraction on hardware. We need abstraction on models, but their models already have abstraction and separation of concerns because there are aspects and abstraction of aspects of reality. And function must be understood, abstracted, you must know what's going on. And then there are two problems, two very different problems. One, which is, are all these abstractions consistent? Okay, which is what Brooks called do the right thing, do the thing right. Okay, and then you need apply math, proofs, formal method for doing that. Okay, checking the consistency of your abstractions, which is important, but it's only one side of the picture. The other side is that does it do the right thing? Which is really, is it close enough to reality for the purpose you're trying to pursue? And that can only be checked through testing. Okay, to check with whether it's close to the reality that you want to address. And so, of course, the story of software is really trying to progress toward better abstraction and separation of concern. So we can see that there is, if we look back at history, there are three main key way of doing that. The first one is the historical approach, which is the idea that somehow the composition of the model with the functionality somehow compile, is completely intertwined. Okay? So it's typical when you're programming Fortran, C, or you're doing control automation, it's the way you're doing it. And why it's the way you're doing it? Because it's probably the most efficient way of doing it. Okay? But of course, there is no separation of concern. And then it's very brittle in the sense that it's very difficult to change the functionality or to change the model without rebuilding everything. So when you have something which is small, that's not a big issue. You just drop it and do it again. No big deal. But when you have something larger, it's starting to be very difficult. So this is why I put an end here. It does not mean that people are stopping using and programming that. It means that during the 80s, people discovered that this could not be the solution for all kinds of systems. As soon as the system is bigger, more complex, you cannot do that. Okay? So there has been this object-oriented revolution that started actually during the 60s with the idea of the Simula language. The Simula language, as the name puts it, is that it was built for doing simulation, okay? And then it was seen as a good paradigm for building a program, because the idea is that the model is still there explicit in the code. Okay? So somehow I would say that the composition of the functionality with the model is somehow interpreted by the machine. Okay? Because the model is still there, and so it's easy, or relatively easy, to build a new machine, a new software, by changing the functionality without touching too much the model. Okay, so it makes it possible to modify and to have a better separation of concern between the model and the functionality that you want to provide over this model. And that's the core idea of object-oriented design, programming, and all these object-oriented languages that are there for many years. So it started really in the 70s with Smalltalk, and in an industrial way in the 80s with C++, and generalized to industry with Java in the 90s. But soon enough, there is still a big problem there, is that it's still very difficult to keep a good separation of concerns with technical concerns. Okay? So if you have no technical concerns, I mean, if you are running a single user software on a PC with no fault-tolerant issue, no big deal with performances and the likes, it's very good. But as soon as you have issues such as handling persistency, security, fault tolerance, a performance issue such as speed and the like, then all these things cross-cut to the model and the rest of the program. They are very difficult to isolate. Okay? So the typical object-oriented way of programming, let's say, a bank account, you just want to credit some money, you just the amount of money is just incremented by some value, but then in reality it's not the way it's implemented in a bank. You have to build a transaction to handle persistency, you have to build fault tolerance, you have to take a look on the database, you have to do a lot of stuff that is unrelated to the model and the functionality, but that has to handle these technical concerns that are very difficult to separate. Okay? So what people are trying to do for starting in the 90s is to try to keep a better separation of concern by having one language per concern, and to have this composition still there at the machine in such a way that you can change one without changing the others. Okay? So to have somehow the interpretation of all these compositions. So actually, I tried to come up with something a little bit more formal than that, but I could not do it. But that's the idea of keeping the separation of concern up to runtime. And so my point is that writing software is, or actually will be, composing abstractions described in different languages. Okay. So that's the idea that we have modeling and weaving. Modeling is the idea of separating concerns and abstracting. So by definition, as soon as you have a complex software, you have many models describing many different aspects of your software. And then what you do when you're a software designer is that you take all these different concerns and you try to produce a design for your software that you're going to produce and to be incorporated into a machine. And of course, that's not new. I mean, that's the thing that any designer in the world is doing on an everyday basis, is, looking at some data model, reliability model, and so on, and then in his head try to compose everything to come up with a design model that handles everything. Okay? So what's the issue? The issue, of course, is that in many cases you have variance. You have several security models, you have many platforms, and if you do it by hand, you have to redo this kind of weaving process manually. And because you're redoing it, it's tedious, it's costly, and so on and so forth. So one of the big challenges is to try to automate this weaving process, to try to automate this composition of these many aspects. We know how to separate aspects, we know how to describe them, but it's still an open challenge to compose them in a very, very, general way. Can do some stuff, but not complete. And that's, of course, connected with product lines, because in any software, in any big software today, you do not want just to address one specific version of the software, but depending on the many countries and the many kind of customers you have many, many variants of the software, and you have to handle that with that. So, complex software-intensive system, there are multiple viewpoints and many stakeholders. There are many concerns, including technical concerns. multiple domain expertise, and we need languages to express them, of course. These languages must be make it possible for experts to work in a meaningful way with them. There must be tool support with a lot of things that we know that are useful, analysis tool, code generation, verification, validation, which are still extremely costly to build. And the other thing is that you separate the concern, but at some point, this concern must be integrated. Okay, and that's an issue. So, just to give you a very concrete example of that, there is this JHipster platform nowadays that is very popular for people building internet applications. The idea is that it's a development platform for generate, develop, and deploy Spring Boot plus Angular web application and Spring microservices, which is all the things that are used in industry in a very large scale. And they are using generative approach for doing that. So it's possible to generate a modern web app containing all of that. And we try to count how many languages they are using. They're using more than 40 different languages. More than 40 different languages for this generative framework. Okay? So it means that already people are using these things in a somehow artisanal way for producing stuff that is very, very heavily used in industry. Okay. So the limits of general programming languages, you know them probably, is that they are powerful, but they are not usable by all stakeholders, including non-programmers. The idea of domain-specific languages is that instead of having the Swiss knife, like in the previous talk, you want to have one tool for each task. Okay, and the idea is it's supposed to be easier to use and more efficient. There is this definition and this thing there, which is another lesson we should have learned from the recent past, is that the development of richer or more powerful programming languages was a mistake, in the sense that these baroque monstrosities, this conglomeration of idiosyncrasies, are really unmanageable both mechanically and mentally. I see a great future for very systematic and very modest programming languages. Do you know when this thing has been said? Which decade? Yes. Actually, that's 1972. And who said it? Dijkstra. Okay, so it's not a new idea, of course. So the idea is that DSL is targeted to a particular kind of problem with a specific set of notation, textual, graphical, support, and so on. And it promises more efficient languages for resolving a specific set of problems in a domain, and each concern is described in its own language. The idea is to reduce the abstraction gap. What do we call the abstraction gap? The abstraction gap is the gap between the problem space, what the user wants, and the solution space, what is built. Okay? And so the idea is that, of course, going through the abstraction, you can reduce a little bit this gap. So, DSL have a very long history. They have been there for almost as long as computing has been done. Actually, you're all using DSLs if you're doing some kind of activity that is related to programming. But maybe you do not recognize them yet as DSLs, because they have many different forms, and we're going to see them. And of course, one of the questions that is interesting me is that more and more people are building DSL. How can we help them? So an example of DSL, HTML, of course, is DSL for web markup, CSS for styling, makefiles for all the guys in this room, for building software, regular expression. This one is quite well known. Okay, for pattern matching over strings, graph visualization, notation for chess, which is not really on the domain of computers, but still is very, very used for describing chess. R, which is a DSL for people doing statistics. Okay, DSL is not necessarily a niche language. You have R with more than 2 million users. Okay, SQL for database queries. But they are more than that, because they exist under different shapes. That's due to Martin Fowler, this classification. We can call them external DSLs. For instance, if you get back to SQL, to SQL, the idea is that they have their own syntax and domain-specific tools. It's very nice for non-programmers because you do not have to learn programming to use this particular tool. Okay? It's very good for separation of concern because you have something which is very isolated from the rest of the system you're building, but it's not that good for integration because, you know, building a system, having a part of DSL and the other part in C++ is, you know, there are mismatches. It's not that easy. So the next idea is to have embedded or internal DSLs, which is now possible with some languages that makes it possible to embed somehow a DSL inside the main language. You can have that in Scala or in C#. For instance, here you have in C# an example of actually programming SQL within C#. Okay, so the integration is much better because you're inside one programming language, but at some point you're inside C# and you're switching to SQL. So the idea is that it's very good for the gurus because there are many traps, especially if you're programming that in Scala. In Scala, it's very nice, but you know it's very easy to mix things up. It's very hard for most of the normal users who are not programmers, but the integration is actually excellent because there is an embedding of the semantics. The compiler exactly knows what it is doing. Okay. And then there is a third way of using DSL, which is what followers call implicit DSLs. It's just APIs. For him, APIs are DSLs. And actually, you can turn APIs in something that looks more into a DSL by using so-called fluent APIs, where each call returns the object that you can call again. So it makes it possible to, let's say, for instance, in Java, to program like in SQL in Java by having, that's the implicit one using the API, but you have this version using the Fluent API, and you basically can see something which is really close to the SQL normal syntax. Okay, so that's very good for the programmer. If you're a programmer, that's just your dream, what you're doing every day anyway, because you're using to use APIs. That's very good for integration because there is no question of integration, but it's very bad for separation of concern and for VNV because it's actually very difficult to check that statically. Of course, there are tools, but if you make an error, if you have a mistake here somehow, that's not going to be seen by the compiler, and that's very easy that's very hard from the security perspective because it's very easy to change one of these strings to do something different. Okay. Another example of a DSL, C. C it's also a GPL. So then what's the difference? Okay. In the past, some people say that the difference was that DSL had to be Turing incomplete. That should be the difference, but it's no longer the case. I mean, the community is saying that it's not really the case, and so it's not always black and white. There is a gray scale of what is a DSL, what is not a DSL. Actually, it's not very important. The point is that in reality, people are using many different languages for building stuff, and they are using languages that are fit for the purpose of what they are doing at some specific point. Get back to this example of JHipster, 40 different languages, why they are there, because, I mean, programmers in the trenches, they feel that it's the best way to do it. Okay, there is no big theory behind them, it's just the way they do it. So, where does software go with these DSLs? A DSL program is a three-dimensional abstraction. It's an abstraction from the domain, because it abstracts something from the domain that you're trying to represent. It's domain knowledge that you're trying to represent, and because it is an abstraction, it's wrong. Okay, again. So that's, Newton theory, again, it's not wrong, but it's, it's a good approximation of the physics up to a certain point. Okay, and a DSL, what you can express in a DSL is always that, a good approximation up to a certain point. Okay, then you have an abstraction from the function and an abstraction from the platform, from the machine. And so one thing is that you have to embrace uncertainty. And that's also reflecting some of the previous talk. The idea is that with smaller abstraction that you can master, you know what you do not know. And that's very important. You know the boundaries. you know what are your assumptions, and you know what are the limits. Okay? So you can better know and control what is unknown to you. And then you can apply a rigorous method to uncertain systems to get results that are valid statistically or with some probabilities and so on, to get non-uncertainties. Okay, that's one of the big things I think in computers in the next year is to forget this idea that it's 1 or 0. Okay, but because that's true in mathematics, but it's not true in software and in computers. In computers, you have something that is good enough up to a certain point, but you have to qualify how good enough it is. You have to know how good it is. And of course, for doing that, you have to use rigorous method. There is no other way. So okay, so that was my introduction. It's like in the movie, the meaning of life. The Monty Python. They started with a very smart introduction that actually lasts 1 hour. But of course, mine is much less funny. But that's the point. So now I will jump into the core of this talk. What's my goal? I mean, not just mine, but the goal of the community and my team and so on, which is how to make it possible for the masses, for all the people, and not just programmers. Probably there are many more non-programmers than programmers in the world. So how to make it possible for them to build DSLs and to use DSLs, which is how to make it possible for people to turn their domain knowledge, the thing they know about the world, the rules and the modeling of the world, into stuff that can be used within a computer that is tools. The first thing to realize is that a DSL is software, in the sense that when you're producing a DSL, it's a language, but it's not an abstract thing. If you want it to be useful, it has to be supported by software. Editors, compilers, checkers, interpreters, tools. Okay? And so what we want to do is to have a fabric for producing these tools. Okay? Not producing them by hand, but producing them using some engineering method. And because they are software, they suffer from all the same things that normal software does suffer, which is versioning, variance, and of course separation of concerns and compositions. Just to give you an idea of why they have variance and version and so on, the typical life cycle of a DSL, if you look at what people are doing, it starts typically with a very simple configuration mechanism. You have this very huge library, very complex, so you're going to provide a way for user to configure this library. Okay? Let's say video processing. You take the FFmpeg, and you have many options, many possible options for doing video encoding. So it goes more and more complex. So typically, what you do is that you have a configuration file. Okay? That is a way to avoid repeating all these command line options. So the command file contains a sequence of options equals pair values, one for each line, and then you have comments, and then you have conditionals, and you have macros, and then you have loops, and soon enough you turn it into a Turing-complete language. Okay, and people do not even realize that they are doing that because it's helpful, it's practical, and it's easy, and then they end up with a Turing-complete language. So that's for variance, for versioning. So DSL do evolve. They start from something very simple, and if you look at well-known languages such as PHP, for instance, it started as a very simple way of making it easier to provide HTML pages. Okay? And then it evolved as a big monster doing plenty of stuff in a weird way. Another thing is variance. In a single DSLs, you may have different variants for different purposes. One well-known example is state charts. State automaton. There are more than 50 different variants of state chart that has been reported. That differs on whether you are allowed what kind of transition, whether you need embedded states, substates, and the like, and many different constructs. And there are more than 50 different variants. Okay. There is variance on the concrete syntax, whether you're using graphics, text, and so on. But there is also variance in the semantics. There is this well-known example of inner and outer transition priority that has been described in this paper by Jürgen Dingel and others. You have this state chart here, and at some point there is the event E, and when the event E happens with this state chart, what is the next state of the state chart? If you're using UML, it's going to be S4. If you're using Rhapsody, it's S5, and if you're using Stateflow, it's going to be S6. That sounds strange, but actually, if you look deeply into it, all these tools have a very good reason for that. It's not an error, it's design. The reason why it's there, for instance, with Rhapsody is because people are using that as the main way of describing the dynamic of systems, and so it makes it possible to have interrupts, basically. Whereas in UML, the idea is that state charts are connected to object-oriented design. And if you want to use the state pattern, then the structure of the state pattern makes it necessary to have this way of this inversion of priority there. So it makes complete sense. Is it really a problem? No. I mean, you just have, if you have a code generator, you just have to handle this variability. It's not that difficult. It's just people who are doing that using product line for more than 20 years. So it's not a big issue. But you do not, it's impossible to ignore. Okay? So for instance, the way people from product line would model that is through what they call a variability model, saying that there is this state machine here. There might be different choice for the syntax. The structure can be either simple or hierarchical. There might be the presence of initial state, final state, and so on. And there might be semantics with either inner priority or outer priority. So it's easy to model and actually to build a tool where you can choose what is the configuration of your language that you want. Okay. And then I would like to mention that when you have several tools, when you have several DSLs, you want them to cooperate. So there is this GMOC initiative that has been launched by my colleague Benoît Commal. The idea is that to have tools and methods for interoperable, collaborative, and composable modeling languages, and there is a tool within the Eclipse framework that does that, but I won't enter in the detail of that. So the idea is that to go from craft to engineering of DSLs, from supporting a single DSLs to supporting multiple DSLs, with editors, parsers, simulators, compilers, and checkers, refactoring tools, converters that are very, costly to build each time for each DSL. So we must do some kind of reuse there to support multiple DSL that interact together. They have several flavors, variants, and they evolve over time. We have product line of DSLs. So our goal is to ease the definition of tool-supported DSLs families. How to ease and validate the definition of DSLs and their tools, how to correctly reuse existing tools, and basically to bring the external design, DSL design abilities to the masses using the object-oriented paradigm, and actually using this notion of DSL for building DSLs. The idea is that DSL is just a software, so there are many different concerns. You can see the fact that there are compilers, checkers, interpreters, editors, and so on, as different aspects of a DSL, different concerns that must be described with their own languages that you must compose. So it's just using the idea of DSL at the meta level, if you wish. So that's the Eclipse modeling galaxy with many different kind of tools for handling that. So I won't enter in the detail of that. Just a very small one, a very small example of what we are doing. It's called Mélange, a meta-language for modular and reusable development of DSLs, the PhD thesis of Thomas Degel. And the idea is that to build DSLs out of other DSLs, okay, to reuse DSLs, part of DSL. So he has defined an algebra by which you can slice a DSL, compose DSLs, and combine DSLs, basically. The idea is that these DSLs are described with abstract syntax and semantics. Semantics can be denotational or translational or interpretative somehow, operational. And then you can consider these as legacy artifacts, and you build languages by combining parts. So the idea is that you can merge these parts to provide languages and compose with part of these languages. And you have a number of operators, such as merging languages, inheriting languages by extending them with new concepts, and slicing languages by taking a part of the language but not the rest. Okay? And the idea is that when you're building a DSL, typically there are parts that you want to reuse. For instance, the part that is the expression language, additions and multiplication and the like. It's stupid to recreate it from scratch each time. So let's take a language that already has them and reuse that part. Okay, that's the basic idea of what we are trying to do. So I don't have time to go into the details, but basically the idea is that you compose a language by composing parts, written in different languages. And if you want to add some stuff, such as an extension of for a finite state language machine with simple guards, then you add stuff and you import new stuff to create a language. It's not just the static part, but it's also come with the semantics. And what we call the semantics here is very operational in the sense that it's a part of a compiler or a part of an interpreter that is integrated with the rest. Okay. But it could be also part of tool, part of a checker or whatever. Okay, so I will skip that because it's starting to be the end of this presentation. So there is this website of Mélange and so on. It's open source. It's written within EMF, Extend, and so on. Okay, and the question is that does it work in practice? Okay, so there is this saying by Linus Torvald that I like very much. Talk is cheap. Show me the code. So here's the code. So these are examples of tools of DSL-based tools that have been built with this Eclipse environment. Not just our tools, because it's very large and we are using many different kinds of tools. But for instance, here something which is dedicated to a collaboration with INRA, which is how to model farms, basically. My colleague called it the co-DSL for handling cause, and that's the idea of modeling a farm with connection with meteo provisions and knowledge about crops and the like, and making it possible to optimize the usage in a farm in a way that is meaningful for the farmer. He is able to describe his parcels and the way they are connected and so on. Another example is water flood prediction here. Yet another example is a NabLab environment, which is there, which is used by people trying to do some kind of some simulation. You can see that you can do some beautiful mathematic-like simulation there, and that's a DSL. There is syntax and semantic, which is fully defined within Eclipse, that you can provide a LaTeX view and another view which is a graph view of the same thing. So actually it's technology that is working. It's still a little bit prototype somehow, but it's already usable, and there are many users who are actually using that. Okay, so there are some open challenges. We still have a huge diversity and complexity of DSL relationships. Far beyond the structural behavioral element, you have also refinement, decomposition, and separation of concerns, and zoom in, zoom out into details. There are many issues around live and collaborative metamodeling, how to build DSL in a better way. And there are also the idea, which is very important, is that what I've been saying from the beginning is that there is domain knowledge, meaning that there is some expert who is not a computer scientist, who knows something about the world, and we are going to help him define his language for providing a specific model for a specific problem. Okay? So it's a priori knowledge. And we know that there is this very successful other way of building models, which is learned models, learning model out of data. And one of the big things we think is to try to compose a priori knowledge given in the term of the kind of model I've been talking from the beginning, with these learned models. And that's very useful for many kind of application where you need actually a composition of a priori knowledge with learned data for a particular implementation. And then there are many different things that you want to do here. So I jump to the conclusion where here the big challenge is, this slide from supporting a single DSL to supporting multiple DSLs and a product line of DSLs, families evolving over time and the like. And one of the big issues is, of DSL, of course, is that if you try to build, 40 different languages, you do not want to pay 40 different language development from scratch, because otherwise it's impossible, it's too costly. So you need to reuse existing parts and to compose existing parts. Okay. So my final slide, which is a blatant advertisement, because actually it was just trying to sell my book. Okay. So if you're interested into the details, just buy the book. I'm getting rich by writing books, as you know. But it's not just my ideas. Of course, it has been developed by many colleagues in my teams, and that is the diverse team at ERISA in area. Thank you very much.